I am Linus Torvaldis, and I pronounce Linux, Linux.
Hosting and bandwidth provided by the Blue Box Group. Check them out at bluebox.net. This episode is sponsored by Component One, makers of Widgmo. If you need stunning UI elements or awesome graphs and charts, then go to widgmo.com and check them out.
Don't panic, they'll be paid for most of us.
Hey everybody, and welcome to episode 54 of the JavaScript Jabber Show. This week on our panel we have Tim Caswell.
Hello.
Jameson Dance.
Hi guys.
Joe Eames.
Hey there.
Merritt Christensen.
Hey guys, what's up?
I'm Charles Max Wood from DevChat.tv, and we have two special guests this week. We have Dave Herman.
Hey there.
And Ariya Hidayat.
Hello everyone.
And these guys are so smart that we brought them back. So if you're interested, we'll put links to the episodes that they were on. David was on when we talked about his book, Essential JavaScript. And Ariya was on when we talked about Phantom.js.
Effective JavaScript, yeah.
Effective? What did I say?
Essential.
Essential? Well, it's an essential book on effective JavaScript. How's that?
Good save.
Good recovery.
At least you didn't say defective JavaScript.
No, that's what I write. I'm really good at writing defective JavaScript.
It would be nice if there's a book about essential on defective JavaScript.
Yeah, I also want to announce really quickly that FluentConf has given us a discount code. So if you want to get 20% off your registration for FluentConf, just enter JavaJab, that's JAVAJAB, and you'll get 20% off when you register for FluentConf. All right, well, let's get started. This is going to be a really, really interesting topic, and it's something that I've wanted to know more about for a long time, and I just haven't delved as deeply into it as I would like to. And that is, we're talking about parsing JavaScript and ASTs and language grammars. So, do one of you guys want to actually explain what all of that means?
Ariya, do you want to give it a try?
I think you should go first, Dave.
I should go first? All right, let's see. So, we're all programmers. We've all seen what source code looks like, but of course, usually source code is just represented as this big flat string, just a sequence of characters. So, parsing is kind of the first step necessary to being able to, for a computer to be able to do anything with your code. So, it starts with this big string, and somehow it has to figure out, well, what does this string mean, and what am I supposed to do with it? So before it starts actually trying to do anything with it, the first thing it needs to do is just try to figure out what the structure of the program is. Just figure out all of its component parts. And basically it just converts it from a string into a data structure that's easier to write code over. It's easier for a program to deal with. So parsing is that process of taking a string that represents some sort of input format, some sort of language or format, and turning it into a data structure. Language grammars, the other half of the title of the show, that's sort of a way of specifying the particular format of some syntax or another. So each language has its own format, and somehow you need a way of saying these are the possible things that you can say in this format, and this is what they're supposed to look like. So a grammar is a way of really precisely saying this is exactly what the syntax looks like for this particular language. And then it turns out that the two connect to each other because grammars are so nice and precise that it turns out you can build tools that automatically take one of those grammars and just spit out a parser for you automatically, so you don't actually have to implement the parser by hand. And there's many, many, many years of research that went into making that work, but that's actually pretty stable research. That was done back in I think it started in the 60s. I think it really started getting stable in the 70s, and by the 80s it was sort of seen as a pretty well solved problem. So grammars are this nice way of describing a syntax. Parsers are a nice way of recognizing a syntax and turning it into a data structure. And then there's these things called Parser Generators that can take a grammar and give you a parser. Does that make sense?
I think that makes tons of sense. You talked about how you use a grammar to describe the syntax. Where do the semantics come from? So that's just like saying what are legal strings in your programming language, basically, right?
Mm-hmm.
So what actually gives those meanings?
Depending on who you ask, so in my personal opinion, that's where the real fun begins in programming languages, is once you get past the syntax and start talking about what the meaning or the behavior of programs are supposed to be. I'm not sure how much we want to actually get into that in this particular episode, since we're talking about syntax, but semantics is kind of what happens after you've got that data structure, which is known as an abstract syntax tree. Once you've done the parsing, now the real fun begins, because you actually have to do something with this data structure. And if you're talking about like a language interpreter, it's supposed to run the program, or if you're talking about a compiler, it's supposed to translate that program to another language. And semantics is the way that we specify what the correct behavior is, or what the correct translation would be for a compiler. And there's a ton of different ways of specifying semantics, and that's when kind of the real deep, hairy language research kind of kicks in.
So we've mentioned it a few times, but can you explain what an abstract syntax tree actually is?
An abstract syntax tree is that data structure that spits out the other end of a parser. So it's known as abstract because you can think of the actual syntax that's in the string as being the concrete syntax for the language. That's really what it looks like to us as people, as humans. But the computer doesn't really care. Did you spell function function, or did you spell it fun, or did you spell it lambda? Different languages have different ways of spelling these things, but you can think of those as just kind of skins. This sort of the user interface for programmers. And humans are the only ones who really care about that. But abstractly underneath, you just sort of have this data structure that says, well, this is a function, and it's got so many arguments, and it's got a body and stuff like that. But once you're down at that data structure, you don't really care how specifically it was spelled in the string.
So the easiest way to understand the abstract syntax tree of a JavaScript code is by using the Esprima parser demo. So I built this, and it shows exactly the tree of your code. So if, for example, I have a code called answers equal 42, then it'll say that, hey, there's an assignment expression, and on the left side is an identifier called answer. On the right side is a literal 42.
That's awesome.
I'm going to send the link later on for the parser demo.
Yeah, that's great. I think it's hard just from talking to get a good feel for what the difference is between concrete syntax and abstract syntax, but it really helps to look at examples, and Ariya's webpage is a really great way to just play around with, okay, here's some concrete JavaScript syntax, and what does it look like as an abstract syntax tree?
So have the various JavaScript parsers pretty much standardized on this AST format for JavaScript? Or is that still...
So they all have different formats. If you talk about particular JavaScript engine, I think it follows internally on how the engine itself is written, or rather the parser portion of the engine. So Dave came up with this idea of sort of nice AST that was implemented in SpiderMonkey as a reflection, I believe. Is that correct, Dave?
Yeah, I mean, I basically took the parser that existed in SpiderMonkey and just provided a JavaScript API that spat out the results of it, so that you could, which was a kind of reflection, so that you could reuse the SpiderMonkey parser in JavaScript itself, so that you could take in a string and get out an abstract syntax tree.
And SpiderMonkey is the JavaScript engine for Mozilla?
That's right. It's the one that ships in Firefox.
Are there other ways of seeing what the parser is doing in some of the other ones, like Chrome or Safari or IE?
I don't think so, unless you're willing to dive into a C++ debugger and peek under the hood. But I don't think any of the other engines expose their parser to JavaScript.
So I think even for the case of SpiderMonkey, reflect is not exposed in normal code, right?
Well, it's perfectly safe. Basically what it does is it runs the internal parser, but then it takes the internal C++ data structure that would be unsafe and copies it into a safe JavaScript object. So there's no security risks there. But it actually is using the internal parser to parse the source code.
Is this exposed in Firefox to normal web pages, or do you have to have a special add-on?
It's exposed to add-ons. It's exposed to the browser Chrome, but it's not exposed to web content.
Okay, so extensions can see it.
Yeah.
So you can type reflect.parse and then your JavaScript code, and then it will spit out the tree.
But anyone can run Esprima because that's just written in JavaScript.
Yes, that was the original idea. So I tried to implement the same parser API in WebKit through its JavaScriptCore. It turned out to be quite hairy because if you try to match one JavaScript engine parser format to another, that is not so easy. That was a difficult process.
So, can you guys explain? You touched on the parser piece, and I usually hear another word when that comes along, which is Lexer. Does Lexer typically come before parser, and can you guys touch on what that is?
Yeah, I'm happy to answer that. Most programming languages will typically divide up this process that goes from the source string into an AST into kind of two parts. And like you said, the first one is the Lexer. The Lexer is kind of like a mini parser. It's doing less work than the parser is, but what it's doing is it's taking this string of characters and actually recognizing kind of the little component chunks. You can think of it sort of as an analogy in human language. You can think of it as the thing that tells you what the words are, and then the parser tells you how the words come together to build sentences. So The Lexer is going to say things like, oh, you wrote obj.foo. That's really three what they call tokens, or you can think of it sort of like words. The first one is obj, which is an identifier. The second one is dot, which is a special symbol in JavaScript that has special meaning by itself. And then the third one is another identifier, foo. So the Lexer is just going to say, I have three tokens. I see three tokens here, obj, dot, and foo. And then the parser is going to say, oh, when I have identifier, dot, identifier, that actually represents a property selection from an object. And so it'll build an AST node, an abstract syntax tree node, that represents that structure. So it's actually possible for some languages not to have a Lexer, but it's rare. Usually that's a good way to divide up the work.
Okay.
So let's say that I want to write my own language, and I'm going to be real creative, and I'm going to call it JavaScript. And anyway, so
from Transylvania.
Yeah, and I want to. How would I go about that? Would I just define my own grammar and then, use that to build the parser?
So I can share how I wrote the CoffeeScript parser, if that's useful.
Okay.
So I was working with Jeremy years ago, and he had an existing CoffeeScript parser written in Ruby using some parser generator in Ruby.
Uh-huh.
And the CoffeeScript syntax is actually I think it's context sensitive. I don't think it's possible to properly explain it using one of the formal grammars. And so I think what we did is we hand wrote a Lexer using regular expressions that just broke up the string into various tokens.
You should define context sensitive.
A type. No, we'll get into that later.
No, I won't define it.
But there are many different classes of grammars, and so you have a regular expression, which is actually a family of grammars, and I'm sure Dave can explain it much better than I can, but the context sensitive ones are much harder to do. I don't know of any parser generator that supports those, at least not efficiently.
I think a loose analogy would be like a human language where different words can have different meanings. Even a full complete sentence under different contexts can give you a totally opposite meaning.
So it's kind of like you can't just read the word in abstract. You have to read it in the context of the sentence to know what it means.
Yes,
right. And all parsers need some context. Like, what does this dot token even mean? Well, in JavaScript, dot's actually not that ambiguous, but there are other ones.
Well, you could put a dot inside of a string literal, for example, and that's a different context where dot means something very different.
That's true, but the Lexer would probably catch those.
Right.
Yep, or decimal numbers.
But there are various, like the square brackets, for example. When I was designing my Jack language, there are only so many symbols on the keyboard. JavaScript overloads, and most languages overload. Square can be property access, or it can be an array literal.
Mm-hmm.
And depending on what it means how is it used in the syntax?
The classic example in JavaScript is a forward slash, because it can start a regular expression, but in some cases it's actually an operator.
Yeah, that's a fun one. And that would be one I would try to get the Lexer to do, but then, I don't know, that's hard, because then you have to backtrack in your Lexer, and The certain languages are harder to write parsers for, and CoffeeScript was one of those harder ones. And so when you're designing your language, if you have the freedom to design the syntax, if you want to make your life easy on you, right, design a syntax that's not ambiguous. But those aren't always the easier to use languages.
Indeed.
Yeah, so this is one of the classic trade-offs when you're trying to. So this kind of gets back to I think it was Charles who asked the question of if I wanted to design my own language, how would I go about coming up with a syntax and coming up with a parser? And it's actually a really subtle design question. And one of the trade-offs that Tim is getting at is you can sort of design the grammar of the language to be simpler for algorithms to parse, or you could design it so that it's sort of more pleasant for humans to look at and easier for them to read. And it turns out that humans are a lot messier than computers. So our tastes often run in directions that go completely at odds with what algorithms would really like to see. And so, overloading is a great example of where, okay, humans are really comfortable with brackets meaning different things in different contexts, but that makes the algorithm much trickier because now it has to use additional contextual information to figure out exactly what it's looking at various points. And so some languages have really gone sort of hog wild with context sensitivity. One of the great examples is the C programming language, where you can't even tell like what basic kind of token you're looking at without knowing the full scope of the program and all of the type definitions in the program, basically due to like really fiddly details in the way they designed the grammar. And so, that has trade-offs. Like on the one hand, people like looking at the C syntax and they find that, they find that ambiguity not a problem for themselves and it reads nicely for them. On the other hand, because it's so much harder to write the tools, it's actually pretty uncommon for people to go and write a new C parser because it's so incredibly hard to write a C parser. On top of that, all of those parser generators we were talking about, which can take a grammar and automatically spit out a parser so you don't have to write it by hand, it's pretty much impossible for any of them to generate a C parser automatically, so you end up having to write it by hand. So in practice, all of the C parsers are handwritten. Pretty similar with JavaScript because of that ambiguity with the slash character. It's pretty hard to use a parser generator to automatically give you a JavaScript parser, so people end up having to write it by hand, which means that it takes really smart people like Ariya to actually build a JavaScript parser, and they don't come by every day. So it's a tough trade-off.
So this leads me to two things. First off, you said that humans are messier than computers, and I have 4 kids and 3 computers, and I have to agree. The second thing is it an all or nothing proposition to use a parser generator, or can you use it to get you most of the way there and then kind of deal with the ambiguities on a one-by-one basis?
So that's what I was about to talk about. With CoffeeScript, you can't actually do the grammar using JSON, which is the parser generator we used, because it's just not possible. So Jeremy's idea was he added a layer between the Lexer and the parser that rearranges the tokens that gets rid of the ambiguities. So that's kind of massages it manually.
Yep. So that was also my first approach to build a JavaScript parser in JavaScript, meaning using a hybrid approach. Some parts is generated by some parser generator, and then I try to work around some problem by manually writing some code. But it turned out for JavaScript, you end up writing so much code that it doesn't really make sense to keep the generated code from the parser generator anymore. And that's how I end up with Esprima. So in some cases, if you describe a grammar for, say, a while statement, the grammar for the while statement looks pretty clear. And if you go to the code, sometimes the code is messier. But at some point, you realize that, by just looking at how while statement parsing is implemented, it's not much more difficult, and therefore you just, dump the grammar, and there's no need to feed it to the parser generator to generate the parser anymore, because if you code it carefully, the parser code itself is understandable enough. I don't know if that makes sense there.
No, yeah, that makes sense.
I think basically what you're saying is that because the grammar is a pretty clear specification, it's not that hard to just follow it by hand and write the code yourself.
Right.
Yeah. And another thing is that people often find that when they write it themselves, they can start to hand optimize it. And parsers tend to be one of those things where It doesn't change very often because you don't change the syntax. So once you kind of get it working, then you can go and start optimizing it to try to get better performance out of it and not have to worry about your optimizations needing to be undone in the future because you're not going to be changing the syntax anyway. So when you have like production quality JavaScript parsers, for example, there were some, I believe, historically in the production JavaScript engines that used parser generators originally, but then as performance became more and more competitive in JavaScript engines, they pretty much all ended up handwriting their parsers so that they could hand optimize them.
Yeah, an example would be JavaScriptCore, which is the JavaScript engine in WebKit. It was originally derived from KJS, from KDE, and KJS grammar is described for Bisons, I believe, and then it's generated to C, and then we have to bind it to C++. So there's a bunch of layers there, and you still need to implement some native C++ code to work around some parsing problem. Semicolon, for example, automatic semicolon insertion that requires workarounds almost everywhere. It just doesn't make sense to keep the old generated code.
So that kind of leads into the next question, and that is, as the specification changes for JavaScript, I mean, some of these is just you're essentially adding new tokens or adding new, functions to your list of things that JavaScript can do. And in some cases, like the semicolon injection stuff, it kind of touches everything. So
yeah.
what are the trade-offs? I mean, if you have a parser that you've been able to just generate, and then they introduce, some kind of breaking change, I mean, are you back to square one or square zero? Or
well, the bottom line, like number one ground rule, is you're not allowed to make breaking changes except in extremely in extreme corner cases where you think no code will actually be affected by it. But this is one of the really tricky things about migrating a syntax, or evolving a syntax, is it's really easy to accidentally add something that breaks the rest of the language. It could either break backwards compatibility, or it could introduce an ambiguity where there might be two possible ways to understand some piece of syntax. And that's one of the worst kinds of bugs when you're designing a syntax, because now it's totally unclear what the behavior of the program should be, because the syntax could actually mean two totally separate things. And so one of the nice things about parser generators is, even if you don't use them in production, if you run a grammar through a parser generator and it succeeds at providing you with a parser on the other end, then unless it's some strange esoteric parser generator that can handle ambiguous grammars, which is those are rare, most parser generators will fail if there's an ambiguity. So that's actually a way to tell, okay, we definitely have an unambiguous grammar. There's no possible string of characters that could be interpreted in two contradictory ways. But it's really surprisingly tricky, and ASI is one of the worst ones. Automatic semicolon insertion is one of the worst ones. Actually, it's probably a good moment for a public service announcement. When you design your next programming language, please don't use automatic semicolon insertion. It's just more trouble than it's worth. It's going
Don't worry, I'm not.
a really difficult language to parse, but on top of that, it's going to lead to endless Twitter wars between people arguing about whether they should use it or not. So just don't bother.
So
I think
So
Golang
Dave-
has it, but you're not supposed to put them in your actual written code. It just adds them for you when it compiles. There's something weird about it with Golang.
Go?
But they avoid the debate. Yeah, don't they?
Go actually has similar problems. They chose different policies to JavaScript. I could be wrong about this. I'm not an expert at Go, but from what I understand, they actually have some similar kind of hazards to JavaScript, where like in JavaScript, if you say return and then an expression, but you put a new line in between them, famous hazard, where you think that's a return with an argument, but it actually gets a semicolon inserted. I think in Go, people will have to correct me after the show if I got this wrong, but if you do a function call where the function returns another function and you want to call that again, so f, left paren, right paren, left paren, right paren, if you put that second pair of parens on the next line, I think it actually inserts a semicolon between them.
Ooh.
So that's different from JavaScript, which doesn't insert a semicolon, but that's sort of a similar hazard. So in my opinion, semicolon insertion ends up being kind of too hazardous. I think you can introduce syntaxes where they're not based on semicolons, but there aren't these kinds of ambiguities or it's not exactly an ambiguity, but it's just a human confusion, an easy confusion for humans. But doing it through automatic insertion of semicolons just seems like it's always more trouble than it's worth.
So because beginners,
I agree.
Yeah, beginners usually cannot figure out the automatic semicolon insertion rules. So I always joke around that it's called semi-automatic semicolon insertion.
It's a semi-automatic weapon.
That's right. You can pull the trigger as many times as you want, and it'll keep shooting until you're out of bullets.
So it doesn't correlate to what you think it's doing.
Yeah. So
Speaking
Dave,
about syntax change again, for example, that syntax change that Dave mentioned, that sometimes you don't need to tweak the syntax very much, or you just pass it to the parser generator. But there's also syntax change that will cause major disaster. For example, one of the nice things about C is you cannot have nested function. There cannot be function inside a function. So if the next version of C language, let's change the syntax so you can have nested function, that will be just nightmare.
Mm.
What are some of the problems that it's going to cause for C? Syntactically.
Well, I mean, you need to understand and rewrite all those parser again, right? Because those do not understand that, yes, you can have function inside a function.
Oh, so it's just going to be a lot of work to update all those parsers. Mm-hmm. Yeah. The worst case scenario is when you introduce something where it actually causes an ambiguity. And that's the one where you might not even notice. And I've seen it happen where we tried to add syntaxes to the ECMAScript standard, and it took a while for somebody to even notice, oops, that introduces an ambiguity.
Oh, so there's not a way you can automatically detect that?
That is one of those fun computer science questions that the general question of give me any grammar whatsoever and tell me if it's ambiguous is actually it's mathematically impossible to build an algorithm that can give you that answer
in
finite
time. Does that
time.
into the halting problem or something?
Yeah, through a series of really complicated proof, but essentially it ends up being like the I think it went through this classic problem called post-correspondence problem, or forgetting it now. It was like PCP was the shorthand for it, but I think that was the way it was proved, and then that can be reduced to the halting problem. Anyway, the long story short is you can't write a general purpose algorithm for any grammar, but for certain subclasses of grammars you can. And so that's why if you have a parser generator that works for a certain subclass of grammars, and there's all these different families that Tim alluded to earlier, like there's LL grammars, LR grammars, LALR grammars, there are all these weird technical names for different subfamilies of grammars. Each one of those you actually can produce an algorithm that can prove whether a grammar is ambiguous or not. So typically, the real parser generators can actually do that for you because they only operate on these subsets.
So how much of language design is limited by people by the language designers trying to make their lives easier? Because I look at it totally from the outside. Like, I just want this feature and I have no idea what it takes or how much work it'll be. It'll just be really cool. Does that happen a lot where you'll just reject things because they'll be really hard to implement, even if they'd be a cool or useful feature?
I've done that a few times. With my new language I'm designing, I have this constraint that it must be an LALR or whatever the default in JSON is grammar, so that I can always use the generator to check my grammar and make sure it's not ambiguous. And there have been many features that I wanted to add, and the grammar's like, no, don't do that. And so I move around the grammar definition, and I cannot find a way to make it unambiguous, and so I just don't allow that feature in the language. One that I've been having trouble with lately is argument destructuring, which is a really cool feature, but it's kind of tricky to do.
Mm-hmm. Yeah, we've run into similar things with the Rust programming language, where again we were trying to keep it so that the syntax doesn't get too complicated, so that it's easy to build tools for Rust. Because that's you have to remember when you're designing a language that you serve many, many different customers, and certainly yourself as the implementer is one customer. But simplicity of implementation also affects tool writers, and those tool writers may not be yourself. And the easier you make things for tool writers, the easier you ultimately make things for developers, because developers are going to use those tools too. So even though there might be something that kind of has an immediate benefit for a developer because as a programming feature it's nice, if it hurts the ability of tool writers to write tools, that could ultimately indirectly hurt developers, or in the longer run hurt developers too. So there's a lot of constraints you have to keep in mind at the same time. On the other hand, I tend to still be willing to violate even my own ground rules that I set for myself. Like, okay, we want to make it easier for tool writers, but oh man, this syntax is just too nice. We'll make an exception here, and we'll make it a little harder for the tool writers. They'll still cope. Tool writers are smart people. They'll figure it out.
I guess it's like an opportunity cost, right? Like if the syntax is nice enough that more people use the language, then you'll have more tool writers and things like that.
So,
it's tough because you're also predicting what people are going to do in 10 years. And, when my language actually takes the world by storm and a million people want to write tools for it, that's so far into the future, it's actually hard to predict what it's going to look like.
I want to go back to something that we've kind of talked about, but didn't really, we didn't talk about as far as like what it actually means. So we talked about kind of what a grammar is, but how is a grammar actually defined?
I'm glad you asked this because this is something that I think is really a great general purpose tool for people to learn. And I think the analogy I want to make is for regular expressions. So regular expressions are just this weird little language that people learn. And I mean, the first time you look at a regular expression, you think, okay, computer science people have really lost their minds. Like this is the weirdest, most arcane little thing I've ever seen. That people talk about it as write once, read never. And it is a really weird little language, but it's so powerful and it's so concise that people use it constantly to the point where they just write little grep command lines and do little one-off regex because they're just so powerful. And so it's actually like it's worth it to put in that effort to learn regular expressions because it's so powerful. But it turns out that regular expressions are actually nowhere near as powerful as grammars are. Grammars are sort of the next step up in power for being able to describe a class of syntaxes. I mean, regex and grammars are really doing the same basic thing. They're saying, here's what a particular syntax should look like, and then you run a recognizer to actually parse it. The thing is that the class of syntaxes that a grammar can recognize is far, far more expressive than the class of things that a regular expression can. So it's worth it to learn the notation of grammars, because it's just so much more expressive. And then once you kind of learn that, you can use that for all sorts of things. Like, for example, if you want to create a new configuration file format for your application, or you want to describe some network protocol where you're sending things encoded in strings between, over the internet. There's all sorts of things where people need to describe a syntax format, and regex are just not powerful enough to do the job. And the other cool thing about grammars is that they're still less powerful than just writing a regular program. And so there's sort of this nice sweet spot in between. So the notation is known as BNF. It stands for Backus, Naur form, named after two famous computer scientists. And so taking the time to learn BNF, I think is a really valuable skill for programmers to learn.
And how does one learn these arcane secrets of which you speak?
That's a good question. I think a lot of BNF is covered in, I think probably most compiler textbooks will cover BNF. You can probably get a lot of material just from Googling it, because it's such a common, tool in computer science that there's probably a ton of literature just online. The other thing is, like, to understand BNF, BNF itself is almost like a tiny little programming language, and it's for the most part, a really simple little programming language. You basically define a bunch of functions and they can call each other. And that's really all there is to it. The one hard thing that's conceptually tricky that you need to get your head around before you get to that point is to be able to think recursively. And that's a skill a lot of people don't have. They aren't born with. It certainly took me a whole bunch of training before I felt comfortable with recursion. And BNF grammars are defined, all using recursion. So for that, I'll just throw out one textbook that I particularly love. It's not in JavaScript, so you have to be willing to play with an esoteric parenthesis-heavy language, Racket, which is kind of a Lisp-like language or scheme-like language. But the book is called How to Design Programs, and their website is htdp.org. And the whole text of the textbook is freely available online. And that's a great introduction to thinking recursively. And I think it's a great precursor to being able to understand BNF.
Yeah, that was one of your picks last time.
Oh, was it? Okay. I guess I'm too obsessed with that book. Awesome. But I really do love it.
That's a good sign.
So it could be overkill. Like, if you feel that you already understand recursive functions, you actually shouldn't have too much of a hard time being able to read BNF, being able to write BNF. And I would just Google it.
Classic example is write BNF for a math expression. So it has to understand, different operators and their precedence. And you can try it to parse simple mathematical expression and see how it goes.
Yeah, so my understanding is that you define expressions and then you tell it how to recognize the expressions based on the tokens that make it up in a grammar.
Yeah, that's pretty much it.
Mm-hmm.
And then, basically what it does is it says, okay, I recognize this expression, and so then it takes the arguments to that expression, and it breaks those expressions up into its tokens, and that's how you get the abstract syntax tree of your program.
Right, and that's also where the recursion shows up, because to define what an expression looks like, well, an expression could be an addition expression, which has a plus in it, but it also has two other expressions. So the definition of an expression includes parsing another expression or two other expressions.
Right, and the expression can be a single token like a number, or it can be another expression which is 10 times 10.
Right,
exactly.
Right.
Yeah, that part's easy. The hard part is sticking to the rules of whatever subset you're using. Like some of them don't allow left recursion, and some of them, if you don't have an operator precedence for your infix operators, then it just blows up. And so, I mean, intuitively, a BNF is very easy to read, but writing one is a little harder.
Yeah, that's true, because the general rules of BNF actually don't prevent you from creating ambiguous grammars, and so there's all these subsets of the possible grammars that prevent you from ever saying something, from ever writing an ambiguous grammar, but understanding the rules of how to stay within that subset is much trickier. And that definitely takes some practice, and it takes playing with the tools. This is actually something I mentioned before. The research was kind of seen as done by the 80s or 90s. One of the things I think they didn't work on back then was really making the tools easier to use. So when it blew up, it would give you these just incomprehensible error messages. And the state of the art in that hasn't gotten a whole lot better. And that's something I would love to see people do more work on is, okay, we understand how parsers work, but can we actually have parser generators that help you debug the problem when you made a mistake in your grammar?
The error messages you get in JSON, the one that CoffeeScript and my language use, they're useful, but if you don't understand the table that it's building internally, they're utterly meaningless. It's like in state 47, I have this shift reduce conflict. I'm like, okay.
Yeah.
And that means what?
This was my experience as well. So as I switched from Parser Generator to Recursive Descent Parser for Esprima, I found out that debugging is much simpler because you can just insert debugger somewhere and then watch the call stack and finally understand what's wrong there, as opposed to some cryptic methods and there's no call stack at all.
So tell me about recursive descent parsers. I have not yet figured these out. My plan is to write one after my grammar is stable. How do they work?
I think, Dave, you want to explain that?
Sure, I'm happy to give it a try. Actually, I think recursive descent parsers, even though the name sounds scary, are sort of like, to my mind, they're the first way you would think to implement a parser, and they sort of follow the structure of the grammar most naturally. So if your grammar says that an expression can be either a number or an expression followed by the plus sign followed by an expression, then you write your recursive descent parser that just says, okay, let's look at the token. If it's a number, we're done. Return, a literal node. Otherwise, just recursively call the expression parser, then look for the plus token, then recursively call the expression parser. Now we've got 3 nodes, put them together, and you're done. And so it's just sort of like a recursive function that does what the grammar says to do.
My favorite example is a
go ahead.
While statement in JavaScript, because while statement is pretty simple. You have a test and a body, and the entire construct itself is that you expect a keyword while, and then it has to follow by open bracket, and then expression, close bracket, and then the statement. So in your parser, you simply write expect some keyword, expect this bracket, and then parse the expression. There where it goes recursively to the other function. And then after that, you close it, and then go recursive again, parsing a statement. That's all you get for a while statement.
So recursive descent kind of by itself is, I think, the cleanest and most natural way to write a parser, following the grammar that specifies what it's supposed to look like. The couple places where it can get tricky are first of all, when you deal with infix operators, dealing with the precedence of those operators is tricky. So you have to know when to keep looking for more arguments and when to return. So that part's a little bit tricky. But you can kind of follow your nose and figure it out. It's actually a fun problem to work on. But it's a solved problem, but it's one of those that's fun to like, I'm not going to look up the answer. I'm going to see if I can write this program myself. The
Didn't
other
Hartford,
part, yeah, he has a paper on that, which is basically just showing here's one way you could write that algorithm that was published in the 70s. Here's one way you could write that in like if I was writing a parser in JavaScript that was doing precedence parsing. And that's one way to do it. I actually found that code kind of hard to follow. But so precedence parsing can be one challenge. The other challenge is if your language doesn't support recursion very well, then you can blow the stack if you have too deep of a nested program that you're parsing. So then actually taking your recursive program and turning it into one that's iterative, that only uses loops and built-in stacks, is kind of a royal pain. So for a simple recursive descent parser where you don't really worry about it, where you're like, if the input program gets too big, we'll just blow up, then you don't have to worry about it. But if you start doing things like, I think we ran into this with Emscripten, where we wrote it in JavaScript, which doesn't have very deep stacks. And Emscripten these days is parsing, million-plus line programs. And so there were times when it just fell over because of the size of the input.
Nice.
I guess that could happen. I just never thought a program would be that big.
Well, when you think of a human writing it, you don't think of it being that big. But when you think of it as I got to parse any program that comes in, it could even be one that was generated by somebody else's code. Suddenly you could imagine it getting a whole lot bigger.
So you could also definitely use a hybrid approach. In Esprima, for example, all the function block statements, I use recursive descent. But as soon as I hit expression like binary and unary, then it switches to simple stack-based parser. Shift and unshift, and that kind of thing.
That's the nice thing about handwriting it.
Yep, that's the pattern that every JavaScript engine uses, I believe. Even SpiderMonkey switched to that trick.
Mm-hmm.
Just like in V8 and JavaScriptCore.
Yeah, and that makes sense because you don't imagine that you're going to have so many deeply nested functions. I mean, let's say your stack blows out at 3,000. Do you imagine that you're going to have 3,000 deep nested functions? But you could imagine a really, really big little operator expression, particularly if it was one that was generated by some other compiler. Those could actually get deep quicker.
Yeah.
So I want to talk about this from the perspective of the humble JavaScript developer, someone who isn't a language implementer, because we have lots of experience with, Tim and Ariya and David are all experienced with language internals, I guess. But what does this stuff mean for someone who's just writing applications? Is this useful just in a general, like, the more you know, the better off you'll be kind of way? Or are there some practical benefits that you can get from knowing more about this stuff?
As Dave alluded earlier, I always see that the benefit is more on the tooling side. Yes, syntax tree is fun, but the fun part is what will you do with that, right? So the classic example is you can build static code analysis like JSLin/JSLin, or you could build a JavaScript minifier. Uglify is the well-known example in this case. So it's really on what kind of set of tools that people can build as soon as you get parser and those grammars and syntax tree.
But I think another place that's good to think about using grammars and parsers for is that not every syntax is actually a full-fledged programming language. And the example I mentioned before is a config file format. And maybe you'll just reuse an existing config format like JSON or JSON plus comments, which we all wish JSON had. But little things like that crop up in programs a lot, especially if you're doing anything with external storage. You're saving some files on the file system, or network protocols where you're communicating between different things. And again, you can always reuse existing formats, and then if you do it in JSON, you just reuse JSON.parse. But it does come up where it's like, well, we need to write this, and maybe JSON just isn't the right syntax for the people who are writing this file format. It needs to be handwritten, and it needs to be in a format that we find easier to read and write. Or maybe JSON is too verbose, and there's like some more concise syntax we can come up with. So I think these things do come up, and it's a useful skill to have. And the other thing is, like, I don't know if people have heard that famous Jamie Zawinski quote. Some people look at a problem and think, I know, I'll use a regex. And now they have two problems.
Yeah.
That quote, the inspiration for that quote is really that when a regex is the only tool you have, you start to think that it'll solve everything. And there are some things that a regex just isn't powerful enough to solve. And the next step up from regex is grammars. So it's good to know what the next step of power is up from regex so you can recognize better, oh wait, in this instance, a regex is not the tool for the job. It's not the one that's going to solve my problem.
That's the answer to all those
to
questions about parsing HTML with regexes.
Yeah.
Don't do it.
Yeah.
Not a regular language.
The other thing, as a humble JavaScript developer, right? Like, I don't come from a computer science background, but so these kinds of things enable like the templating languages like handlebars, right? Where you can even add kind of your own functions into these DSLs that we use in the web every day, like Angular. You can hook in and make your own directives, but these are ways to hook into the compiler, and they end up being a lot more expressive. So as a humble JavaScript developer, you're using these kinds of things all the time, and understanding them better means you're going to be able to use them better.
Mm-hmm.
Yeah,
Another
I've had a
example
couple
is... Sorry, I'll just give this example really quick. Another example is jQuery, where you basically have something a lot like CSS embedded in a string, and there are definitely arguments for and against doing that kind of thing, inventing your own DSLs and embedding them in strings. But I think jQuery has obviously gotten a huge amount of mileage out of that, and they never could have done that if they didn't have somebody who could write a parser for that embedded language.
And you're referencing what's passed to for the humble JavaScript developer. You're referencing what's passed to the jQuery object, like whether it's an HTML string or a CSS selector, right?
Right, exactly. So you say $sign of the string, .foo space .bar or .foo space hash bar or whatever. That's like this little language that has a syntax, and somebody had to write the parser to parse that string to be able to make jQuery work. And if you want to write the next jQuery, well, you're going to have to write a parser.
Yeah, I've had a couple situations in my career come up. We needed to do some text searching. We used Lucene to do that, and that has all this stuff around, whatever you're indexing, the text you're indexing, you can get better information out of it if you write, a custom Lexer and parser using the tools that it provides and some other tools that are available. And so that really made a big difference to understand those concepts. And to be honest, at the time, I didn't understand them very well and got some introduction to them. And also, you can solve some business problems with writing a DSL that isn't necessarily for programmers. Mm-hmm. I've done that before as well.
One of the fun things, the next COBOL. One of the things I learned from the Lua community is they have a library called LPeg, which is basically, I guess it's a parser generator, or maybe it's an interpreter, but you basically just give it grammars and then feed it strings, and it's like a more powerful regular expression engine, but they're not regular, they're full grammars. And you get the tree as your match. And I always wish I had something like that in JavaScript readily available, where I could just write a small grammar and match against it the same way I can just write a regular expression and match against it.
You should totally write that.
I'll do a Kickstarter for it. How's that?
So,
good idea.
Are there any other aspects of this that we want to cover before we get to the picks?
I guess one thing I also wanted to point out is that an AST is kind of like this key to like a massively bigger kingdom of things you can do in your program. It's like if I hand you the source code to some JavaScript, well, we've got eval, so you can pass it to eval. But other than that, regex, there's only so much you can do with regex. As soon as you can actually turn that into an AST, there's all sorts of interesting things you can do with that data structure. But on the other hand, it's good to have a healthy respect for just how complicated that space is. So like, you could write an interpreter for JavaScript with that AST. You could write a static analysis engine for JavaScript with that AST. You could write a compiler to compile a JavaScript to something else. And every one of those topics is like this big, huge topic that's really complicated. And incredibly fun and worth learning about, but also like I've seen some people who kind of get their hands on an AST and they write their first static analysis and it's like totally broken. So it's good to recognize that these are complicated areas and fun topics to learn about, but also very big topics.
Yeah, but very powerful topics. Like, for example, one thing I had to do was write something that lets you basically precompile handlebars templates, but also be able to dynamically pull in partials, etc., from other files using AMD. The only way I was able to do that is get access to the handlebars abstract syntax tree and figure out what were partials, come up with a path, pull them in. So for someone who doesn't, I'm not a programming language expert by any means, I was able to take advantage of this abstract syntax tree and add a whole another level of power to our application.
Mm-hmm.
Yeah, that's what I'll call as augmenting the existing syntax, right?
Awesome.
Or features.
Nice. All right. Well, I'm going to wrap this up and get us into the picks. Merrick, do you want to start us off with the picks?
I'm just going to pick these guys that we're on the episode with because this is like one of those episodes that's incredibly humbling, and being on the show with these guys is pretty awesome. So that's all I got.
Awesome. Joe, what are your picks?
So a little bit ago, Origin had a sale and had Mass Effect 3 on for $10, and I haven't bought it and played it yet. I played the other ones. So I'm going to pick Mass Effect 3. I've been playing it recently, really enjoyed it. Also, there's a Coursera course that just barely launched this week, so by the time this gets published, it'll be like 2 weeks ago, but I think you'd still be able to sign up for it. It's called A Beginner's Guide to Irrational Behavior, and it's done by Dan Ariely. I think that's how he pronounces his last name. And he's the guy who wrote Predictably Irrational, which is a very popular book about human behavior and how irrational we are, although we're predictable at it. And it's a whole Coursera course about it, I don't know if it's 4 or 6 weeks, but about human behavior. They call it economic behavior or something. I can't remember what the scientific term for it is. Anyway, it's really, really interesting stuff. So I'm gonna pick those 2.
All right. Tim, what are your picks?
I don't know. I just think programming languages are fun. I don't really have any picks in particular other than if you ever think programming gets boring, go write a language. It won't be boring anymore.
Nice.
And you'll learn things about the language that you didn't ever realize, things you just took for granted. So, yeah, I guess that's my pick. Go write a language to learn one.
Awesome. I think I'm going to go write Ruby script and coffee, and then I can get the same dumb questions that I get about JavaScript. So JavaScript, is that Java? No. CoffeeScript, is that coffee? No.
That's awesome.
Anyway, who hasn't given the picks yet? I guess I'll go, and then we'll have our guests go. Jameson, did you give us picks?
I did not.
Okay, we'll let Jameson go then.
So I've got 3. My first one is a dumb blog called Thumbs and Ammo. It's just a little Tumblr picture blog, and it's pictures of action movie stars where they take their guns and they Photoshop thumbs in place, so it looks like they're giving people thumbs up. It's pretty awesome. It made me giggle. My other one is totally a guilty pleasure. I make fun of dubstep a lot, but then sometimes I like fall into it anyways. So it's this dubstep album called ISM by Savant, I think is the artist. It's kind of like chiptunes-ish dubstep, but it's totally like awful music. It's still good to listen to though. I enjoyed it. And then my last one, I haven't been here in a while, and I came back again, and it was so good. I went to vimcast.org again, and I forgot how amazing his accent is. So if you use Vim and you want to learn more about it, and you also want to just be entertained by listening to someone speak English in a great accent, go to vimcasts.org. Those are my picks.
Nice. All right. So I'm going to pick a couple of things. One of them is a little bit self-serving, and that is, well, it's self-serving in the sense that it's something that I'm doing, but it's something that obviously I'm giving back to the community. We are starting the iFreaks show next week, and that will be on iOS programming. So if you have an interest in that, then go to ifreakshow.com, and the site should be up by the time this gets released. It's not there now, but anyway, go check it out. We've got some awesome panelists, and it's going to be a lot of fun. My other pick is Mosey. And Mosey's actually a company that I used to work for. It's here in Utah. but it's an online backup company. The thing that I really like about it is that I know the algorithms that they use to store and everything because I did tech support for them, and I'm really comfortable with that and the fact that my data isn't going to vanish from their servers. But it's also not here as a local backup. So I can use Time Machine on my Mac and get local backups, but heaven forbid if somebody broke into my house and stole my machine and the hard drive with it, or if the house burned down or something, I wouldn't be totally out of luck. All the stuff that I've worked hard on is still out there, and I can just restore it to a new machine. So I typically think it's a good idea to have a local backup and a remote backup, and then you're just covered for all the just in cases. David, what are your picks?
All right, my first pick is the micro USB cable that I bought from Walgreens because I lost my last cable, and the only one they had was bright pink, and so I needed one, so I just bought it, and I had no idea what a benefit it would be to have a bright pink micro USB cable, because wherever I go, I never forget it. It's always the most noticeable thing in the room, so I never walk out without it.
Nobody's going to steal it as well.
Yeah.
I don't know. I have some kids that would like it.
My other pick is something that I'm super excited about. We've been working on this in my group at Mozilla Research, along with the Mozilla JavaScript engine team, and we just put out our first release of this subset of JavaScript called ASM.js or ASM.js. And what ASM is basically we've just said, look, here's a subset of JavaScript. It's totally just JavaScript. It works in every JavaScript engine. But if you can generate code in that subset, we can optimize it like nobody's business. And so what we did was we worked with the game company Epic, who make the Unreal game engine, and we helped them port their Unreal Engine 3 to the web. And we're talking about over 1 million lines of C++ code being ported to JavaScript through the Emscripten compiler and generating ASM.js on the back end, and showed that in the latest nightly builds of Firefox, it gets performance that feels exactly like native performance. So there's a little YouTube video of it online where you can see some of the fly-throughs. We haven't actually released any of those demos. I think at least one of them is going to be released publicly where people can play with it.
Yeah, I was going to ask, when can I play Unreal Tournament in my browser?
So I think they're just
I saw the GDC videos, but...
Yeah, I think they're just going to be demos. I don't think there's actually going to be like an Unreal full game that's released, but I'm not sure about that. But anyway, it's a technology demonstration. We're just trying to show that the web is actually ready with no plugins to run games the same way native can. And with ASM.js, we're closing the gap to native performance to the point where our benchmarks are showing we're within 50% of native speed at this point. So I'm very excited about what we're showing the web can do.
Interesting. All right. Ariya, what are your picks?
So my first is related to that Coursera course about human behavior. It's a book called Beyond Office Politics, The Hidden Story of Power, Affiliation, and Achievement in the Workplace from Linda Sommer. So this tells you why a person behaves certain ways and how you can work together with that person once you know their motivation and objectives. Very fantastic book, typically for engineers to understand the social interaction between people. So the second one is a library that I'm having fun with. It's called Library and a Tool. It's called Istanbul from Yahoo. It's a JavaScript code coverage, and it tells you exactly what part of the code that you didn't test. That includes all the branches and statements and function and so on. So famous quote from Dev Glass from Yahoo, YUI team: if you think Jaslyn hurts your feeling, wait until you use Istanbul.
All right. Sounds great. Well, we'll go ahead and wrap up the show. Thanks for coming, guys. It's been a really
thank you so much.
Talk about this.
My pleasure.
Thank you.
Yeah, we'll be on next week. Well, you guys will be on next week. I'm going to be gone next week, but we'll see y'all in a week or two.
See ya.
All right.
Bye-bye.
Bye.
Bye. Have fun.